Harmonic distortion in transform systems is our research project topic. Our group members are Nidup, Ugyen, Moon, and Isura. So I'm going to speak about the way of introduction. So in we are talking about the uh, causes, effects, and mitigations in harmonic distortion and in transformer systems. So harmonic distortion refers to deviation of voltage or current wave from the pure sinusoidal shape. It occurs when non-sinusoidal current generated by nonlinear loads interact with power systems. So let's see why it is matters in transformer systems that harmonic distortions. Why that? What are the problems that in transformer systems? It leads to excessive heating by increasing the copper and coal losses. In the same way, it causes for the vibrations and noises. In the same way, it impacts to the durability of the transformers also. So now I am going to about what are the sources of harmonics. Uh, they are nonlinear loads. So uh, rectifiers, converters, and VFDs are the examples. So in the same way, draw current and non-linear pulses are also sources of harmonics. So our project objectives are identify the causes of harmonic distortions and analyze the effect of the transform performance and explore the mitigation techniques using LT space simulations. So I'm invited again to complete the methodology.
To continue with the presentation, I'm going to talk about methodology. So we have used the LT spice to simulate our model, and we have observed two load conditions, one with the linear load which has purely resistive and 100 ohm. Other one is we have used non-linear load with bridge rectifier and capacitor having capacitance of 1500 microfarad. So Fourier analysis, we have used Fourier analysis to measure the total harmonic distortion, and the main harmonics that we have observed are third, fifth, and seventh order harmonics. Next, please. So simulation and data analysis. In our simulation, we have used the same source voltage and transformer parameters in both the cases, linear and non-linear cases. So we have made the simulation to run until the steady state before the data collection, and we have used the FFT plot to visualize the waveform distortions. So from our simulation, we have observed that for linear load, clean sinusoidal wave of total harmonic distortion 0.039% is observed, and for non-linear loads, a pulse current with the total harmonic distortion of 67.29 is observed. So the results that we have obtained is validated with the IEEE standards and literature sources.
Thank you again. I'll be presenting on the results and discussion session. So as we can see here, this figure shows the difference between using a linear and non-linear load. When you connect that linear load, just a simple 100 ohm resistor, output waveform came out really clean, almost a perfect sine wave. Actually, like those, results were already stated by Ugen. Just without wasting much of time, I'll just say like we changed the setup non-linear load using a bridge rectifier and 1500 microfarad capacitor. Waveform got quite distorted. You can clearly notice how uneven it becomes in our, the research project, and the THT shoot up to about around 67%. Both were done using same transformer, as already stated by Ugen. So next slides. Now moving on, this level of THT clearly goes above IEEE 519 standard, which allows only about 5% for voltage and 8% for current. So it proves how non-linear loads can seriously affect power quality. This pattern also matches what Duan and my colleague mentioned, that non-linear loads are main reason for harmonic in low voltage systems. Next slides, please. Here we compare our results with what already published in research papers. Those are very, detailed in our, research project, which aligns really well. The harmonic pattern we got from our FFT analysis is almost the same as ones shown in those, studies. So that basically confirms our LT spice simulation is quite accurate and reliable. Please next slides. And finally, just to wrap up, high THT means more losses and overheating, as it was, explained clearly by Isura in the introduction section, and that can shorten transformer's life. Efficiency also drops, and the insulation gets teased over a time. To fix that, we can use filters, delta Y connections, or balance the loads better. So overall, keeping THT low is really important if you want stable and efficient transformer performance. So next, Moon will wrap up our,
Thank you, Nido. My name is Chanyeon Moon. In conclusion, our project's key findings are best summarized by the visual evidence from our LT-SPICE simulation. As you can see in the waveform comparison, we visually confirmed that nonlinear loads are the primary source of harmonic distortion. The clean sinusoidal current drawn by the linear load shown on top is fundamentally altered into the sharp pulsed waveform below when a nonlinear load is introduced. This distorted waveform is the critical issue. It confirms that even a single device can inject significant harmonic pollution into the system, which explains why the cumulative effect of many such devices poses a real risk to transformer health and power quality. Next, please. Therefore, as our results demonstrate, applying effective mitigation techniques is not just a recommendation, but a necessity to prevent transformer damage and efficiency loss. Our research identified several solutions. While active and hybrid filters offer the best performance, passive filters and K-rated transformer provide practical, cost-effective alternatives for many systems. Looking forward, the future of harmonic control lies in smarter technologies like AI-based adaptive filtering and real-time monitoring. Ultimately, this project reinforces that adhering to standards like IE519 and implementing these solutions is our professional responsibility as engineers. Next, please. And this is our references, and thank you for listening.